We'll start in 1 minute. Today we're going to cover section 9.2 on how to solve quadratic equations by completing the square. And on tomorrow and then on Thursday, we'll do the test 3 review. And test 3 is on Friday. There are 2 playlists on YouTube that cover the test 3 material, the Math 1108 test 3 review sheet videos, and then another playlist, Math 1108 Chapter 7 and Chapter 8 material, which has the Test 3 material on it. Okay, we'll take a look at section 9.2 today. Okay, you've seen quadratic equations before, and we're going to solve quadratic equations by completing the square. So a few sentences. Solving a quadratic equation by completing the square involves some preliminary work. But once that work is complete, the equation can be solved by using the square root property. Yesterday during class, we talked about the square root property. The expression completing the square in this context simply means to create a perfect square trinomial. And recall that a perfect square trinomial is the result of squaring a binomial. And by now you know that there's a lot of emphasis put on perfect square trinomials in this class, in this course. So a couple of examples. These types you've seen before. If we square the binomial x minus 3, that means to multiply x minus 3 times x minus 3. And when you multiply the 2 binomials, you get x to the second minus 3x plus 9. And that simplifies to x to the second minus 6x plus 9. X to the second minus 6x plus 9 is a perfect square trinomial because it's the result of squaring a binomial. And another example, if we square the binomial 4y plus 5, that means 4y plus 5 times 4y plus 5. And when we multiply those 2 binomials, we get 16y to the second plus 20y plus 20y plus 25. And then combine the like terms by adding, we get the perfect square trinomial, 16y to the second plus 40y plus 25. Okay, so since a perfect square trinomial has characteristics that are known under appropriate conditions, a perfect square trinomial can be constructed. So I'll do the following example that illustrates what to do when completing the square. So as I mentioned before, completing the square is synonymous with creating a perfect square trinomial. Okay, so if we begin with x to the second plus 6x, then what we're going to be concerned with is the case when the coefficient of x squared is 1. So we observe that we have a coefficient of 1 on the x squared term. And then if the coefficient of x squared is 1, we move to step 2. We compute 1/2 of the coefficient of x. The coefficient of x is 6. So we find 1/2 of that number. 1/2 times 6 is 3. And then we move to step 3. In this step, we square the number that we found in step 2. The number we found in step 2 is 3, so we square that. 3 to the second equals 9. And then we move to step 4. We add the number that we found in step 3 to the x squared plus 6x. And when we add 9 to that number, we get x to the second plus 6x plus 9. And x to the second plus 6x plus 9 is a perfect square trinomial. And we know that it's a perfect square trinomial because when you factor it, the two factors are identical. And if two factors are identical, you can write it as a single binomial raised to the second power. Okay, so that is what's behind solving quadratic equations by completing the square. It involves creating a perfect square trinomial. And then after creating the perfect square trinomial, we're going to write it as a binomial squared. Okay, we'll do some intermediate exercises before actually solving equations by completing the square. So in these examples, for each of these, we're going to do the same thing that we did in the previous example. We're going to create perfect square trinomials out of terms that have x squared, an x squared term and an x term. Okay, so for x squared plus 2x, just observe that the coefficient of x squared is 1. Then the coefficient of x is 2, so we take 1/2 of 2. 1/2 times 2 is 1. And then we square 1. 1 squared is 1. So if we add 1 to x squared plus 2x, we now have a perfect square trinomial. And if we factor a perfect square trinomial, the two factors are identical. In this case, x plus 1 times x plus 1. But when we're solving equations by completing the square, we want to write it as a binomial squared. Okay, so that's all there is to it. So we'll do the monotonous thing of practicing for a while. Okay, the next one, x squared minus 2x. The coefficient of x squared is 1. Then this time, the coefficient of x is negative 2. So we take 1/2 of negative 2, which is negative 1. And when we square the number negative 1, we get positive 1. So we're going to add 1 to x squared minus 2x. So x squared minus 2x plus 1. This is now a perfect square trinomial. And when we factor it, the two factors are identical. The two factors are x minus 1 and x minus 1. But we're going to write x minus 1 times x minus 1 as x minus 1 to the second. Okay, the arithmetic can get a little more challenging. So let's complete the square on x squared plus 7x. So first note, the coefficient of x squared is 1. Okay, then step 2, we compute 1/2 of the coefficient of x. The coefficient of x is 7, so we compute 1/2 of 7. And we get 7/2. Then we're going to square that number. So when we square 7/2, that just means 7/2 times 7/2. If you want to write that out, you can, if it helps you to remember. 7/2 times 7/2. And then when you multiply two fractions, you multiply the numerators. 7 times 7 is 49. And then you multiply the denominators. 2 times 2 is 4. Okay, so we're going to add 49/4 to x squared plus 7x. And this is now a perfect square trinomial. This might seem a little more difficult to factor, but I'll point out some things. Whenever you're creating a perfect square trinomial going through this process, there's always something that you can look at to determine what the two factors are. Well, since the perfect square trinomial has x squared in it, the identical binomials have the term x in it because x times x is x squared. Then both of the operators in the perfect square trinomial are plus signs or addition. So that means each of the two identical binomials have plus signs. And then the potentially challenging part is knowing what number to put here and here. Well, the number that we put is the same number we got when we took 1/2 of the coefficient of x. So 1/2 times 7 is 7/2. So that means we're going to put 7/2 in each of the binomials. So x plus 7/2 times x plus 7/2. When we're solving equations by completing the square, we always want to write x plus 7/2 quantity squared, or whatever the binomial factor is squared. Okay, the next example is similar in a way to the previous one. We want to find how to create a perfect square trinomial out of x squared minus 13x. Okay, so the coefficient of x squared is 1. You might wonder why I'm always pointing out that. Well, if the coefficient of x squared is something besides 1, then the process of creating a perfect square trinomial is more involved than what we're doing. So, and for our purposes, when solving quadratic equations by completing the square, we will always be able to get to the point where the coefficient of x squared is 1. Okay, so since the coefficient of x squared is 1, we take half of the coefficient of x. The coefficient of negative 13, 1/2 times negative 13 is, well, I should write it down correctly, sorry. 1/2 of negative 13 is negative 13/2. Okay, then we're going to square negative 13/2. And that just means negative 13/2 times negative 13/2. If you can read my writing. And negative 13/2 times negative 13/2 is positive 169/4. Okay, so we're going to add (169/4) to x squared minus 13x, and this is now a perfect square trinomial. So that means the two binomial factors are identical. So the left term in each binomial is x, because x times x is x squared. And the perfect square trinomial has a minus sign and a plus sign, so we know that we have to have minus signs in the two binomials. Then how do we know minus what? How do we know what to put here? Okay, so just like in the previous example, 1/2 of the coefficient of x, which is negative 13/2, that's what we're going to be putting here, but we write it as minus 13/2 in each binomial. Remember, you can always verify that you are factoring correctly by multiplying the factors. So you can pretty much tell by looking that if you multiply these two binomials, you get the perfect square trinomial. And then we want to write, instead of a product of two identical binomials, we want to write it as a single binomial squared. Okay, so by now, if you've been following, you know how to create perfect square trinomials, but we'll do a couple more. This one will probably seem easy by comparison. The coefficient of x squared is 1, and we take half of the coefficient of x, so we take 1/2 of 10. 1/2 of 10 is 5. Then we square 5. 5 squared is 25. And then we add 25 to x squared plus 10x. And we have completed the square, or synonymously, we have created a perfect square trinomial. And the two factors, well, each of the binomial factors has to have an x in it, because x times x is x squared. And then we know what else to put in those two binomials, because 1/2 of 10 is positive 5, so we put plus 5 and plus 5. And then we write it as x plus 5 squared. Okay, the last example, x squared minus 24x. The coefficient of x squared is 1. So in step 2, we take 1/2 of the coefficient of x, 1/2 of negative 24, which is negative 12. And then we're going to square negative 12. And when we square negative 12, we get positive 144. Okay, so we're going to add positive 144 to x squared minus 24x. And this is now a perfect square trinomial. That means its two factors are identical. So each of the two factors has to have the x term in it. And another key observation, since the perfect square trinomial has a minus sign and a plus sign, the two binomials must have minus signs. Okay, so 1/2 of negative 24 is negative 12, so that's how we know how to fill in the binomials. So we have x minus 12 and x minus 12. And x minus 12 times x minus 12, we want to write it as x minus 12 squared. Okay, so if you follow those tedious exercises, now we can start solving quadratic equations by completing the square method. Okay, so I'll remind you of what I read to you when we were first starting. I'll just read it. It says, solving a quadratic equation by completing the square involves some preliminary work. And once that work is complete, the equation can be solved by using the square root property. Okay, so the preliminary work, in this case, we're going to add 9 to both sides. This is an equation, so we want to solve it. And whenever we have an equation, we can do the same thing to both sides of the equation, provide what it is that we're doing is not illegal. So we can add 9 to both sides, and we get x squared plus 10x. I'm going to leave space because we're going to create perfect square trinomial. So that's why I'm leaving space between the 10x and the equal sign. But when you're showing your work, like on a test or something, you won't want to do all of the work in a single step. You'll want to show some intermediate steps. Okay, so in the next step, we can just, in this case, we can just observe that the coefficient of x squared is 1. If the coefficient of x squared is not 1, then the next step would involve dividing every term on both sides by the coefficient of x squared, because we want to get the quadratic equation into a position where the coefficient of the squared term is positive 1. Okay, but we already have that, so now we can create a perfect square trinomial on the left-hand side by adding the appropriate number, and whatever number we add to the left-hand side, we also must add to the right-hand side. Okay, so just like we did in the exercises, we take 1/2 of the coefficient of x, which is 5, and then square that number. 5 to the second is 25. So we're going to add 25 to both sides of the equation. So we'll get x squared plus 10x plus 25 equals 9 plus 25. And x squared plus 10x plus 25 is the binomial x plus 5 squared. 9 plus 25 is 34. And now we can solve this equation the way we did yesterday in section 9.1. We can apply the square root property. So if x plus 5 squared equals 34, then applying the square root property, we get x plus 5 equals positive and negative square root of 34. And then subtract 5 from both sides. We get x equals negative 5 plus and minus the square root of 34. If you want to write the solution separately, you can. One is negative 5 minus the square root of 34, and the other one is negative 5 plus the square root of 34. Okay, we'll do a few more examples. Okay, solve this equation by completing the square. Y squared minus 8y minus 22. So first, add 22 to both sides. So we get y to the second minus 8y equals 22. The coefficient of the y squared term is 1. If it isn't 1, we want to divide every term on both sides by whatever that coefficient is. And then we can create a perfect square trinomial. So we take 1/2 of the coefficient of y. 1/2 of -8 is -4. And then we square the number -4. And we get positive 16. Okay, so in the next step, we're going to add 16 to both sides of this equation. We get y squared minus 8y plus 16 equals 22 plus 16. And y squared minus 8y plus 16 is a perfect square trinomial. So we can write it as the binomial y minus 4 to the second. And 22 plus 16 is 38. And now we apply the square root method, the square root property. Y minus 4 squared is 38. So when we apply the square root property, we get y minus 4 equals positive and negative square root of 38. The square root of 38 cannot be simplified any further, so our two solutions are y equals 4 plus and minus the square root of 38. Okay, we'll move on to the next level a little bit. So we haven't seen this situation yet. We have the quadratic equation. It's not in standard form, but it's still a quadratic equation. Negative 3x squared plus 36x equals 33. This time the coefficient of x squared is not 1, so we want to get it into the position where we do have a coefficient of x squared that's 1. So we can do that if we just divide every term on both sides of the equation by -3. Okay, so we'll divide every term on both sides by -3. We get 1x squared minus 12x. I'm going to leave space. Whoops. And then this is equal to 33 divided by -3 is -11. Okay, in the next step, we create a perfect square trinomial on the left-hand side, and whatever number we need to add to the left-hand side, we also add to the right-hand side. So first we take 1/2 of the coefficient of x, 1/2 of -12 is -6. And then when we square -6, we get positive 36. Okay, so we're going to add 36 to both sides of this equation. And we get x squared minus 12x plus 36 equals -11 plus 36. This is now a perfect square trinomial, x squared minus 12x plus 36. So we can write it as x minus 6 squared. And the right-hand side, -11 plus 36. Okay, so now we can apply the square root property. If x minus 6 squared is 25, then x minus 6 is positive and negative square root of 25. And in the next step, I'll do two things at once. I'll add 6 to both sides and also simplify the square root of 25. So we get x equals 6 plus and minus 5. We can simplify further because the square root simplified to an integer. So we have to list the solutions separately. One solution is x equals 6 minus 5, which is 1. And the other solution is x equals 6 plus 5, or 11. The next example will be a little stickier, but it won't be too bad. We have the quadratic equation in the variable y to the second minus 5y minus 3 equals 0. So to start with, we'll add 3 to both sides, so y squared minus 5y. Leave some space, right, equals 3. Then we note that the coefficient of y squared is 1. So we can proceed to the next step. We find 1/2 of the coefficient of y. 1/2 of negative 5 is negative 5/2. And then you square negative 5/2. And when you square negative 5/2, you get positive 25/4. Okay, so we're going to add 25/4 to both sides of this equation. And we'll get y to the second minus 5y plus 25/4 equals 3 plus 25/4. Okay, so there's some fraction arithmetic on the right-hand side that we have to deal with. The left-hand side is a perfect square trinomial. So when we factor the perfect square trinomial, we'll just get a single binomial squared. We'll come back to this. On the right-hand side, before we can add fractions, we have to have a common denominator. So the least common denominator is 4. So we will rewrite 3 over 1 as 12 over 4, and we're adding that to 25/4. And then on the inside of the parentheses, in other words, the binomial squared, well, the binomial has to have a term y in it. And we also know that it has to be minus something. Okay, so the number that goes inside the parentheses is the same that we got when we took 1/2 of negative 5. 1/2 of negative 5 is negative 5/2, so that means we're going to write minus 5/2. So y minus 5/2 squared equals 12 over 4 plus 25 over 4. So let's go ahead and add those fractions. We get 37/4. Okay, now we can apply the square root property to the binomial y minus 5/2 squared equals 37/4. So we get y minus 5/2 equals positive and negative square root of 37/4. And the square root of 37/4 can be simplified a little bit. So in the next step, I'll add 5/2 to both sides. So we get y equals 5/2 plus and minus. And then think of the square root of 37/4 as the square root of 37 over the square root of 4. And then finally, in the next step, we can write the final answer, y equals 5/2 plus and minus the square root of 37, which cannot be simplified any further, but in the denominator, the square root of 4 simplifies to 2. Okay, so those are the two solutions. Okay, we'll do some more examples that are a little bit more involved, but not by much. Okay, so we'll solve some more equations by completing the square. So solve 5x to the second plus 15x minus 50 equals 0. So first we'll add 50 to both sides, because when we're solving by completing the square, we want the x squared term and the x term on one side of the equation and the constant on the opposite side. So step one is add 50 to both sides. Just out of habit, I put a space between the x term and the equal sign. Okay, the next step. So I haven't done this yet in a YouTube live session, but type in what the next step is. You can just do that in a few words. So I'll wait until you reply. Type in what the next step is. Is anybody there? Okay, so I'll type in the answer. This is what I'm looking for. So divide every term on both sides of the equation by 5. And we want to do that because we want the quadratic equation to be in the position where the coefficient of x squared is 1. So we can get that if we divide every term on both sides by 5. Okay, so we'll get x squared plus 3x equals 10 when we divide every term on both sides by 5. Okay, the next step is creating the perfect square trinomial step, or the completing the square step. We can add a number to both sides of the equation so that the number that we add to x to the second plus 3x is a perfect square trinomial. Okay, the coefficient of x squared is now 1, so we take 1/2 of the coefficient of x. 1/2 of 3 is 3/2. And then we square that number, 3/2, and we get 9/4. So we add 9/4 to this equation on both sides. So we get x squared plus 3x plus 9/4 equals 10 plus 9/4. The left-hand side we want to write as a binomial squared. And on the right-hand side, we want to write a single fraction. Okay, so on the left-hand side, some binomial squared, and we know that the term x has to be in it because x squared is x squared. On the right-hand side, we want to add 10 plus 9 over 4. Before we can add those, we have to have a common denominator. So we're going to replace 10 over 1, or replace 10 with 40 over 4th, 40 fourths, 40 over 4. So 40 over 4 plus 9 over 4. Okay, and the binomial that we're squaring, we know we need to have a plus sign because the perfect square trinomial has 2 plus signs. And then how do we know what number we're adding? Well, we add the same number that we got when we took 1/2 of the coefficient of x. So 1/2 of 3 is 3/2. So that means in the binomial we have x plus 3/2. Okay, so we have x plus 3/2 quantity squared equals 49 fourths when we add the two fractions. Okay, so now we can apply the square root property to this. So I'll put that up here. When we apply the square root property, we get x plus 3/2 equals positive and negative square root of 49 fourths. And then in the next step, I'll subtract 3/2 from both sides. And I'll simplify the square root of 49 fourths. The square root of 49 is 7, so we have 7 in the numerator, and the square root of 4 is 2, so I have 2 in the denominator. And we can simplify further because the square root was eliminated upon simplifying. So one of the solutions is x equals negative 3/2 minus 7/2, which is negative 10/2 or negative 5. Negative 5 is one of the solutions. And the other solution is x equals negative 3/2 plus 7/2, which is 4/2 or 2. Okay, so the two solutions are negative 5 and 2. Okay, we'll keep going. 3 more examples. 2y to the second minus 10y minus 32 equals 0. So in step 1, we add 32 to both sides. So we get 2y to the second minus 10y equals 32. Then divide every term on both sides by 2 because we want the coefficient of y squared to be 1. Okay, in the next step, we complete the square. We're going to add a number to both sides of the equation so that the left-hand side is a perfect square trinomial. So y squared minus 5y equals 16. So the number we add is the number we get when we square 1/2 of negative 5. Okay, if you want to write down the arithmetic, you can. 1/2 of negative 5 is negative 5/2. And then when we square negative 5/2, we get 25 fourths. Okay, so we're going to add 25 fourths to both sides. Okay, then up here we'll write the binomial squared. So this binomial is going to be y minus 5/2 squared. And we have to add 16 to 25 fourths. So 16 over 1 plus, I'll go ahead and write it out, 16 over 1 plus 25 fourths. we need a common denominator, which is 4. So 16 over 1 is equivalent to 64 over 4. And 64 over 4 plus 25 fourths is 89 fourths. Okay, so we now have y minus 5 halves squared equals 89 fourths. So we apply the square root property to that equation. On the left-hand side, we get y minus 5 halves. And on the right-hand side, positive and negative square root of 89 fourths. Okay, so in the next step, I'll add 5 halves to both sides. So we get y equals 5 halves, and then plus and minus. The square root of 89 fourths is the square root of 89 over the square root of 4, but I'll just replace that with 2 because we know that the square root of 4 is 2. The square root of 89 cannot be simplified any further than that. So those are the two solutions. So only about 5 minutes left. So you'll make it if you hang on. Okay, on the next one, solve this equation by completing the square. Negative 4x squared minus 20x equals negative 4. Well, we already have the x squared term and the x term on one side of the equation. So now we can divide every term on both sides by negative 4. And we get 1x squared plus 5x. Leave space. Negative 4 divided by negative 4 is 1. In the next step, we complete the square. Take 1/2 of 5, which is 5 halves, and square it. When you square 5 halves, you get 25 fourths. And so we add 25 fourths to both sides. So I sort of skipped a little bit of the work, but you know, and that's okay if you can tell right away. If you take 1/2 of 5, that's 5 halves, and when you square 5 halves, you get 25 fourths. It's okay to leave some of the details out in the writing. Just don't leave everything out. Okay, the left-hand side is now a perfect square trinomial. So we know that it's equal to some binomial squared. And the right-hand side, we're going to replace 1 with 4 over 4. And 4 over 4 plus 25 fourths is 29 fourths. Okay, so what goes with the x inside the binomial squared? Well, it's the same number we got when we took 1/2 of 5. 1/2 of 5 is 5 halves, so that means plus 5 halves. And now we can apply the square root property. X plus 5 halves equals positive and negative square root of 29 fourths. And then in the next step, we subtract 5 halves from both sides. X equals negative 5 halves plus and minus the square root of 29 in the numerator, and the square root of 4 in the denominator simplifies to 2. And the square root of 29 cannot be simplified any further. Okay, there's less than 2 minutes, so we'll at least get started on this one. 2y squared minus 14y minus 8. Add 8 to both sides, so we get 2y squared minus 14y equals 8. Then divide every term on both sides by 2. We get y to the second minus 7y equals 4. Then we create a perfect square trinomial on the left-hand side, y squared minus 7y. So 1/2 of -7 is -7 halves. And when you square -7 halves, you get positive 49 fourths. So we add 49 fourths to both sides. The left-hand side is now a perfect square trinomial. It's y minus the number we got when we took 1/2 of y, the coefficient of y. So it's minus 7 halves squared. And the least common denominator is 4. 4 can be thought of as 16 over 4. And 16 over 4 plus 49 over 4 is 65 over 4. And now we're almost done. Apply the square root property. Y minus 7 halves equals positive and negative square root of 65 fourths. And then the last step, y equals 7 halves plus and minus, sorry, that's not 64, it's square root of 65 fourths. So in the numerator is the square root of 65, the square root of 4, and the denominator is 2. Okay, so that's all we have time for today. Tomorrow we will start the test 3 review. We'll start in about 1 minute. And section 4 today, for the 9 o'clock session, we'll do the first part of the test 3 review. Test 3 is this Friday. There are 2 playlists on YouTube that cover the test 3 material. Under playlists, if you look for Math 1108 test 3 review sheet videos, those videos have examples that are not exactly the same as the ones that we're going to review today and tomorrow. So if you need extra practice, you can look at some different examples on those videos. And there's also the Math 1108 Chapter 7 and Chapter 8 material, which is the Test 3 material. Today we will try our Zoom meeting right as soon as class ends at 9:50 a.m. There might be a minute where there's a lull because I'm going to go to my office for the Zoom meeting. And what I hope we can do is on Friday, everyone can log into Zoom and position your camera so that I can observe what you're doing with your hands. So you can write answers on white paper, and as long as I can see what you're doing, then that's the way that we're going to proctor test 3 if possible. Okay, we'll start the test 3 review. Okay, from sections 7.1 and 7.4. In 7.1, that's the section on restricted values. And we need to know how to find restricted values when solving equations with rational expressions is what was in section 7.4. Okay, so we'll do a couple of problems like that. Find the restricted values, then solve each equation. The restricted values come from the x values that make denominator 0. So one of the restricted values is positive 2. So up here I'll just note what the restricted values are. Okay, so one of the restricted values, we say x cannot be 2. This denominator x plus 1 means x, the negative 1, x cannot equal negative 1. Negative 1 is the other restricted value. And also observe that this denominator, x squared minus x minus 2, is just the product of x plus 1 times x minus 2. So we don't have any more restricted values other than 2 and negative 1. Then to solve an equation with rational expressions, we want to clear the denominators. So in order to do that, we identify what the least common multiple of the denominators is, also called the least common denominator. The least common denominator in factored form is x plus 1 times x minus 2. And in expanded form, the least common denominator is x squared minus x minus 2. Okay, then we were going to multiply every term on both sides of this equation by the least common denominator, either in factored form or expanded form. Either way is okay, but just use the form that is the most convenient. On the left, on the left term, using the expanded form of the least common denominator makes more sense to me. So I'm going to multiply x minus 1 over x squared minus x minus 2 by x squared minus x minus 2. I'm going to write it over 1 so that I remember that x squared minus x minus 2 is in the numerator, and I'm multiplying that by the term x minus 1 over x squared minus x minus 2. Then we multiply the next term, x plus 2 over x plus 1, by the least common denominator. This time I'm going to use the factored form of the least common denominator and write it as x plus 1 times x minus 2 over 1 multiplied by x plus 2 over x plus 1. And then also on the right-hand side of the equation, the least common denominator, x plus 1 times x minus 2 all over 1 multiplied by x minus 1 over x minus 2. Okay, in each of those products, we're going to get a cancellation. From the numerator, the trinomial factor, x squared minus x minus 2, divided by itself is equal to 1. So these cancel, and we're just left with x minus 1. And then plus, over here we have x plus 1 divided by x plus 1. Those cancel. And so we have plus x minus 2 times x plus 2. And on the right-hand side, in this product, x minus 2 times x minus 2, and we're just left with x plus 1 times x minus 1. Now it's just algebra and arithmetic. Multiply the two binomials, x minus 2 times x plus 2. We get x times x is x squared, and then plus x times 2 plus 2x. And then minus 2 times x, and minus 2 times 2 is minus 4. On the right-hand side, multiply those two binomials. X times x is x squared, minus x, and then plus x, and minus 1. So notice both sides of the equation have an x squared term, so we can subtract x squared from both sides. On the left-hand side, the plus 2x minus 2x, those add up to 0, so those are eliminated. And also on the right-hand side, minus x plus x, those add up to 0, so those are eliminated. And let's write down what we have left. On the left-hand side, we have x, and minus 1 minus 4 is minus 5. And on the right-hand side, the only thing left is negative 1. So now we just add 5 to both sides, and negative 1 plus 5 is positive 4. So x equals 4 is our candidate. And then we check the restricted values. 4 is not a restricted value, so we'll conclude that x equals 4 is the only solution. But if you want to make sure, you can always go back to the original equation and replace every x with 4 and make sure that the resulting equation is true. But for now, we'll bypass that and look at another example. Okay, find the restricted values first. Two of the restricted values. Since the denominator is y minus 2, y cannot be 2. This denominator, y minus 7, means that y cannot be 7. And things always usually work out pretty nicely. This denominator, y squared minus 9y plus 14, is just the product of y minus 2 times y minus 7. So we don't make it any more difficult than we have to. So these are the only two restricted values. Okay, the least common denominator is just y minus 2 times y minus 7 in factored form. And in expanded form, it's y squared minus 9y plus 14. Okay, so we multiply every term on both sides of the equation by the least common denominator, either in factored form or expanded form. And the purpose of doing that is to clear the denominators. Okay, so multiply y minus 4 over y minus 2 by y minus 2 times y minus 7. So we'll get y minus 2 times y minus 7 over 1 times y minus 4 over y minus 2. And then minus, break down the minus sign. And this time I'll use the expanded form of the least common denominator, the y squared minus 9y plus 14 over 1 multiplied by 3 over y squared minus 9y plus 14. Then on the right-hand side, I'll use the factored form of the common denominator, y minus 2 times y minus 7 over 1 times y minus 8 over y minus 7. Okay, it looks worse before it looks better, but the payoff is worth it. In this first product, y minus 2 divided by y minus 2 cancels. So in this first product, we did what they call clear the denominator. The denominator is now just 1. In the next product, we clear the denominator by canceling the common trinomial factors. On the right-hand side, clear the denominator by dividing y minus 7 by y minus 7. Okay, so we'll write down what's left. Over here we have y minus 7 times y minus 4. And for the next term, we just have minus 3. On the right-hand side, we have y minus 2 times y minus 8. Then it's just algebra and arithmetic. So y minus 7 times y minus 4, y to the second minus 4y minus 7y, and plus 28 minus 3. On the right-hand side, y times y is y squared minus 8y minus 2y, and then plus 16. Okay, so we'll get rid of the clutter that's in the way. Both sides of the equation have y squared, so we'll subtract y squared from both sides. And we'll combine like terms on the left-hand side. Minus 4y minus 7y is negative 11y, and then plus 28 minus 3 is plus 25. On the right-hand side, minus 8y minus 2y is negative 10y, and then plus 16. So I think what I'll do is I'll just add 11y to both sides. So we get 25 equals y plus 16. And then subtract 16 from both sides. We get 9 equals y. Okay, well that's not a restricted value, so that's a good sign. And if you want to be absolutely certain that there were no mistakes made, you can always check your answer in the original equation. Okay, let's move on then to section 7.5 with a couple of word problems. Hey, this one, Evan takes 3 hours to clean the barn stalls by himself, and Doug takes 4 hours to do the job by himself. How long would it take them to clean the stalls if they work together? Okay, this is we call it a work problem, so equations have the form rate times time equals 1. Okay, so for Evan, we'll write down an equation of that form, rate times time equals 1. And we're told that Evan can do that job, one job, in 3 hours. So Evan works at a certain rate, and in 3 hours, he completes one job, rate times time equals 1. Then we're also told how long it would take Doug by himself. So Doug works at a certain rate, and in 4 hours, he completes the job, one job. We're supposed to find how long it takes when they work together. So Evan's rate plus Doug's rate, well, we don't know how much time it's going to take. So in algebra, we assign a letter or a variable to represent the quantity that we're supposed to find. So I'll use capital T to represent the amount of time it takes Evan and Doug to clean the stalls when they work together. Okay, so eventually we want an equation whose only variable is t. So an intermediate step, solve each of those equations for the rates. Evan's rate is 1/3. He can do 1/3 of the job per hour. Doug's rate is 1/4, which means he can do 1/4 of the job per hour. And then solve this for Evan's rate plus Doug's rate. When they work together, the rate is represented by 1/t. Okay, then in the next step, we can replace Evan's rate with 1/3. I miswrote here. Evan's rate is equal to 1/3. We got that by dividing both sides of this equation by 3. Okay, so in this equation, replace Evan's rate with 1/3. Add that to Doug's rate, which is 1/4. And the sum of the rates is 1/t. T represents the number of hours it would take them working together. Okay, so this is an equation with rational expressions. So we can find the least common denominator and then multiply every term on both sides by the least common denominator. The least common denominator is 3 times 4 times t, or 12t. And you can think of it as 12t over 1 if that helps. Then multiply every term on both sides by 12t. Okay. Then each one of those products will simplify. 12t divided by 3 is 4t. And plus 12t divided by 4 is plus 3t. And on the right-hand side, 12t divided by t is 12. So we just get 7t equals 12, and then divide both sides by 7. T is 12/7 hours. Leaving it as an improper fraction is fine, but you can also say 1 5/7 hours is how long it would take them if they work together. So just leave the units in hours. Okay, so if it's difficult or challenging to know what form the equation takes, well, if the problem describes some task that they're working on, then it's going to be a work problem. The equations have the form rate times time equals 1. Okay, the next problem, number 2, it takes Greg 1 hour longer to walk 12 miles than it takes Chris to walk 12 miles. Greg's walking rate is 2 miles per hour slower than Chris's walking rate. And then it says find their walking rates. Okay, well, this equation, distance is described. Greg walks a distance of 12 miles, and Chris also walks a distance of 12 miles. Time is mentioned. The amount of time it takes Greg to walk 12 miles is 1 hour longer than it takes Chris to walk 12 miles. So we have distance described and time, and rates are also described. Greg's walking rate is 2 miles per hour slower than Chris. So the equation needed for this problem is rate times time equals distance. Okay, so we'll write down an equation of that form for Greg and also for Chris, and then we'll incorporate the required information. We're supposed to find their walking rates. So we assign variables for that. We have options that are equivalent. So how about if I just start with Greg's walking rate. So I'll just pick his walking rate to be X miles per hour. I could have started with Chris and assigned X to be Chris's rate. It doesn't matter as long as the two expressions, as long as the terms that you use convey the information that's given. So Chris's walking rate well, we're told that Greg's walking rate is 2 miles per hour slower than Chris's walking rate. So if Greg's walking rate is X miles per hour, Chris's walking rate is X plus 2 miles per hour. Because we're told in the second sentence that Greg's walking rate is 2 miles per hour slower than Chris's walking rate. Okay, so that seems to make sense. And another key bit of information is that it takes Greg 1 hour longer to walk 12 miles. So we'll deal with that in a minute. But let's go ahead and write down the equations, each having the form rate times time equals distance, one for Greg and one for Chris. Okay, so Greg walks at a rate of X miles per hour. And the amount of time we don't know. Let's just use T sub G for the amount of time it takes Greg to walk 12 miles. And then for Chris is walking at a rate of X plus 2 miles per hour. And we don't know exactly how much time he took, but let's represent that amount of time as T sub K for the amount of time it took Chris to walk 12 miles. Okay, so what's the relationship between Greg's time and Chris's time? Well, we're told that in the first sentence. It took Greg 1 hour longer to walk 12 miles than it took Chris to walk 12 miles. So this amount of time for Greg, that's a bigger number than the amount of time for Chris. It's bigger by 1. So we can form an equation out of this. We can one option, there's 4 options, but one option is subtract the smaller number from the larger number. So in other words, Greg's time minus Chris's time is equal to 1. And we'll come back and use this in a minute. But for now, we'll solve each of the 2 equations for time. Greg's time is his distance, 12 miles, divided by his rate, x miles per hour. Chris's time is his distance of 12 miles divided by his rate, x plus 2 miles per hour. And then these 3 equations, the information from these 3 equations will be combined so that we get an equation whose only variable is x. So replace Greg's time with 12 over x, and we're subtracting Chris's time, but we're going to replace Chris's time with 12 over x plus 2, and the right-hand side is 1. Okay, so we now have an equation with rational expressions. The variable that we want to solve for is in the denominator. Okay, so we multiply every term on both sides by the least common denominator. The least common denominator is x times x plus 2. X times x plus 2. So multiply 12 over x by x times x plus 2. The x's are going to cancel, and we'll be left with 12 times x plus 2. And then we're going to subtract 12 over x plus 2 times x plus 2. This time the x plus 2 factors cancel, so we'll be left with minus 12x. And then on the right-hand side, we don't get any cancellations. Multiply 1 times x plus 2. I'm going to write the right-hand side in expanded form, which is x squared plus 2x. Okay, then we'll do the algebra and arithmetic. So on the left-hand side, we get 12x plus 24 minus 12x equals x squared plus 2x. Notice on the left-hand side, the 12x minus 12x, those combine to make 0. And so we just have 24 equals x squared plus 2x. Okay, so these terms are eliminated, and so we'll subtract 24 from both sides, and we get 0 equals x squared plus 2x minus 24. And we can easily solve this by factoring. One factor is x plus 6. The other factor is x minus 4. This equation has 2 solutions. One is x equals negative 6. The other one is x equals 4. But the only solution that makes sense is x equals 4. So Greg's walking rate is 4 miles per hour. And Chris's walking rate is 4 plus 2, or 6 miles per hour. Okay, there are a couple of ways you can go about verifying that those are the right numbers. You could just put them back into the equations that we formed, and everything will work out pretty nicely. You can also determine the exact amount of time that each took to walk 12 miles. Okay, let's move on then to section 7.6. Okay, section 7.6, solve rational inequalities. Solving this one, this is all set up the way we want. X minus 2 over x plus 3 is greater than 0. 0 is already on one side. And so the endpoints are the intervals that make the numerator 0 combined. I think I said that wrong. The endpoints are the x values that either make the numerator 0 or the denominator 0. The x value that makes the numerator 0 is positive 2. The x value that makes the denominator 0 is negative 3. Okay, so we plot the numbers negative 3 and 2 on the number line. Negative 3 is to the left of 2. And those two endpoints divide the entire real number line into 3 separate intervals. So we have to pick a test point from each interval. In the interval on the left, we'll pick x to be negative 4. And then in the inequality, replace every x with negative 4. In the numerator, negative 4 minus 2 is negative 6. In the denominator, negative 4 plus 3 is negative 1. And negative 6 divided by negative 1 is 6. And the inequality greater than 0, that's true. So that means all of the numbers from negative infinity to negative 3 are solutions. In the second interval, we'll pick a number between negative 3 and 2. We can pick 0 for x and replace every x with 0. We get negative 2. 0 minus 2 is negative 2. In the denominator, 0 plus 3 is 3. And negative 2/3 greater than 0 is false. So none of the numbers in that middle interval are solutions. And then in the third interval, pick any number you want greater than 2. So I'll pick 3. And then in the inequality, in the numerator, 3 minus 2 is 1. In the denominator, 3 plus 3 is 6. And positive 1/6 greater than 0 is true. So all of the numbers from 2 to infinity are solutions. Since the inequality is strictly greater than, there's not an or equal to part. We exclude the x value that comes from the numerator. And we always, no matter what, exclude endpoints that come from denominators. Okay, so graphically we put a parenthesis at negative 3 and shade to the left. Put a parenthesis at 2 and shade to the right. Okay, this says write solutions in algebraic and interval notation. So the interval notation is parenthesis negative infinity comma negative 3 parenthesis, and then union parenthesis 2 comma infinity. That's the algebraic notation. And then the interval notation. The algebraic notation, this part of the number line is x is less than negative 3. And then we write the word or, and this part is x is greater than 2. This is the algebraic notation. Algebraic involves the variable as expected. Okay, this one is a similar process. I'm going to bypass this one. I'll just mention that since this is less than or equal to 0, the endpoint that comes from the numerator, which is negative 1, is part of the solution set. But we always exclude endpoints that come from the denominator. So the other endpoint 5 is excluded. But the process is the same as this, just the two endpoints will divide the number line into 3 intervals. Okay, this one down here, part C, is a little more complicated because there's more endpoints. So we can factor the denominator pretty nicely. One factor is x plus 2. The other one is x minus 3. And so now we can identify the endpoints. The endpoint that comes from the numerator is x equals 5. And we have two endpoints that come from the denominator. One is negative 2 and the other one is positive 3. Okay, then divide the number line into 4 separate intervals. So negative 2 is to the left of 3, which is to the left of 5. So we have 4 intervals to test. Okay, in the interval on the left, between negative infinity and negative 2, I'll pick x to be negative 3. And then I'm going to use the factored form. In the numerator, negative 3 minus 5 is negative 8. And in the denominator, one of the factors, negative 3 plus 2 is negative 1. And the other factor, negative 3 minus 3, is negative 6. A negative number divided by a negative times a negative is a negative number. This simplifies to negative 4/3. And negative 4/3 greater than or equal to 0 is false. So none of the numbers from negative infinity to negative 2 are solutions. In the second interval, 0 is in this interval. Using the original inequality is more convenient when 0 is the test point. When you replace every x with 0, you get negative 5 divided by negative 6. But that's positive 5/6, and 5/6 greater than or equal to 0 is true. So all of the numbers between negative 2 and 3 are solutions. In the third interval, I'll just pick x to be 4. And then I'll use the factored form. In the numerator, 4 minus 5 is negative 9. 4 plus 2 is 6. 4 minus 3 is positive 1. So this is just negative 3/2 when it's simplified, and then negative 3/2 greater than or equal to 0, that's false. Okay, so none of the numbers between 3 and 5 are solutions. And then finally, in the fourth interval, I'll pick x to be 6. And I'll use the factored form again. In the numerator, 6 minus 5 is 1. In the denominator, 6 plus 2 is 8. Times 6 minus 3 is times 3. And 1/24 greater than or equal to 0. This is true. Okay, so on this inequality, the endpoint from the numerator is 5. And that is included because if you replace every x with 5, you get 0 greater than or equal to 0, which is true. So we include 5, so we put a bracket up here when we're graphing it. And the other two endpoints are excluded because they come from the denominator. Endpoints that come from denominators are always excluded. So graphically, we put a parenthesis at negative 2 and a parenthesis at 3, and then shade everything in between. Okay, so the interval notation, parenthesis negative 2 comma 3 parenthesis, and then union bracket 5 comma infinity. That's the integral notation. And the algebraic notation, if x is in this set, it's negative 2 is less than x, which is less than 3. And then we use the word or, and then this part of the number line, x is greater than or equal to 5. Okay, so on the right is the algebraic notation, And on the left is the interval notation. Okay, we'll start the Chapter 8 review material. So sections 8.1 and 8.2. So 8.1 will seem pretty easy compared to what we did in 8.2. So the square root of 81x to the 14th. We're going to assume that x is not a negative number so that we don't need to use the absolute value symbols. Okay, so the square root of 81x to the 14th, both 81 and x to the 14th are perfect squares. The square root of 81 is 9. The square root of x to the 14th is x to the 7th, because 14 divided by the index 2 is 7. The next one, the cube root of negative 125 plus the fourth root of 64. The cube root of negative 125 is negative 5, because the number negative 5 to the third power is negative 125. And then the fourth root of 64 well, this one doesn't simplify to an integer. The largest factor of 64, that's a perfect fourth power, is 16. So we can think of this as the fourth root of 16 times 4. So we'll drag the number negative 5 along. And then the fourth root of 16 is 2. And then multiply 2 times the fourth root of 4. So that's the simplified result. Okay, the next one, the fourth root of 16, that's just the number 2, because 2 to the fourth power is 16, and the square root of 16 is 4, and then 2 minus 4 is negative 2. Okay, in the next example, the square root of 121x to the 10th, y to the 22nd. It's a square root, and 121 is a perfect square because 11 squared is 121. X to the 10th is a perfect square. Y to the 22nd is a perfect square. If the exponents are multiples of 2, then they are perfect squares. So we can just simplify this to 11, x to the 5th, and y to the 11th. We're multiplying those. Okay, the next example is not quite as simple as the last one. Simplify the square root of 98 times n to the 33rd. The largest factor of 98, that's a perfect square, is 49. And the largest factor of n to the 33rd, that's a perfect square, is n to the 32nd. So we'll rewrite this as the square root of 49 times n to the 32nd multiplied by the square root of the remaining factors, which are 2 times n. And then we simplify. The square root of 49 is 7, and the square root of n to the 32nd is n to the 16th. So we multiply 7n to the 16th times the square root of 2n. Okay, in the next example, well, in this case, it's to our advantage if we simplify the rational expression first. 72 over 98 simplifies to 36 over 49. The variable parts don't simplify, but we can write this as the square root of 36 x to the 21st over 49 y to the 14th. Then we can write the numerator as the square root of 36x to the 21st over the square root of 49y to the 14th. And in the denominator, it's going to simplify completely without a radical. The square root of 49 is 7. The square root of y to the 14th is y to the 7th. And the largest factor, well, 36 is a perfect square, and the largest factor of x to the 21st that's a perfect square is x to the 20th. So we'll write it as the square root of 36x to the 20th times x. And then finally we can simplify completely. The square root of 36 is 6. The square root of x to the 20th is x to the 10th multiplied by the square root of x in the numerator. And in the denominator, we already have just 7y to the 7th. Okay, in this part G, also note that we can write the fraction in lower terms, because 250 divided by 16 simplifies to 125 over 8. So we get the cubed root of 125 m to the 30th over 8 n to the 24th. If you want, you can write the numerator as the cubed root of 125 m to the 30th. And in the denominator, the cubed root of 8n to the 24th. But all of the radicals will disappear because the cubed root of 125 is 5. The cubed root of m to the 30th is m to the 10th, because 30 divided by 3 is 10. And in the denominator, the cubed root of 8 is 2, and the cubed root of n to the 24th is n to the 8th, because 24 divided by 3 is 8. Okay, a few more examples. So at the top, simplify the square root of 75x to the 23rd. The largest factor of 75 that's a perfect square is 25, and the largest factor of x to the 23rd that's a perfect square is x to the 22nd. So we can rewrite this as the square root of 25x to the 22nd multiplied by 3 times x. And then the square root of 25 is 5. The square root of x to the 22nd is x to the 11th, and then multiplied by the square root of 3x. That's the simplified result. Okay, on the next one, the fifth root of negative 64x to the 28th plus the fifth root of 32 times y to the 18th. Fifth roots of negative numbers are just negative. So the largest, well, the negative factor of negative 64, that's a perfect fifth power, is negative 32. So we'll write this as the fifth root of negative 32. The largest factor of x to the 28th, that's a perfect fifth power, is x to the 25th, because 25 is a multiple of 5, and then times 2 times x to the third, and then plus, well, 32 is a perfect fifth power, and the largest factor of y to the 18th that's a perfect fifth power is y to the 15th. So we'll rewrite this as the fifth root of 32 y to the 15th times y to the third. And then in the next step, we can simplify completely. The fifth root of negative 32 is negative 2. The fifth root of x to the 25th is x to the 5th, because 25 divided by 5 is 5. And we multiply that by the fifth root of 2x to the third. And then simplify this. The fifth root of 32 is 2. The fifth root of y to the 15th is y to the third. And then we multiply that by the 5th root of y to the 3rd. Okay, so we're about out of time. I'm going to end the meeting or end the session now, and then I'm going to go to my office and I'll start the Zoom meeting and join in for a few minutes. So I'll see you in a couple of minutes.